Hey, good morning, everyone. Good to see you all back. I hope everyone is doing well. We would continue today with the spring elements, but I would like to pause for a minute and review our roadmap that we're going to continue to use for the rest of the semester. You may recall in our first class period, I showed you this slide, and I said, this is the one I always keep with me, because this is the one we're always going to reference to remember where we're at and where we're heading. The good news is today we can look at it and say, we have gone through almost all of these steps. And I say almost because, yes, there are a few things we haven't done yet, because we are looking at a simple element and we're looking at uniaxial. So we're still remaining. The local coordinates are the same as global coordinates. We did not need to look at displacement functions yet, which is another thing we're going to do in chapter 3. But we have selected spring elements and looked at them in assemblage. We did not do step 2, but we were able to define some element relations as far as like how the displacement affects the internal forces, and we related these together for a spring element. We drove the element stiffness matrix and equations for a spring element using the direct method. We learn how to assemble element equation, obtain global equation, apply boundary conditions so that we can solve for the unknown degrees of freedom. We used these degrees of freedom to solve for the internal forces, which we can use to find the stresses or the strains for the spring element. We were able to interpret the results. If you recall last time when we did an example, we were able to see the elements in tension or in compression and how much force was in them. And of course, we applied it to something very simple that rarely you will be working a problem like this using finite elements, but your finite element models may have a spring element. But really the goal of this is to understand the process and how we put it together for a simple element. And we're going to grow gradually. The goal for today is to go back and revisit deriving the element stiffness matrix and equations, again for a spring element. But today we're going to use a different method. All right? So let me clarify here a bit. Deriving element stiffness matrices, of course, and equations. We have 3 methods that we can use. The first one that we used or utilized already is the direct method. Or we can say the equilibrium method for structural problems. Number 2 is the variational methods. Maybe I should put methods and methods. And for structures, we are going to use energy methods. And finally, 3 would be the weighted residue methods. So the one we applied so far is the direct methods. So on the direct method, before we move on, I can say that the direct methods are the simplest. They provide clear physical insight they are recommended for learning the concepts. However, they are limited to deriving. Thank you. FE equations for one-dimensional element, 1D elements, as in springs, bars, trusses, and beams. And in the direct methods, as they apply to structures, there are 2 approaches. A, the force or flexibility method. Yes. Yes. Better. So there is the force or the flexibility method where the unknown, or rather unknowns, are the internal forces. That's why we call them force methods. And B, we have the displacement, or sometimes we call it the stiffness method. Where the unknowns are the nodal displacements. And this is the one we used for our spring element, because the stiffness method or the displacement method is simpler for computation and formulation. So this is the one we used when we used the direct method to derive the spring stiffness equations and the stiffness matrix for a spring element. So if I go back to my three methods, direct methods, force or displacement methods for equilibrium, we've already applied it. Today, we want to apply an energy method to derive the element stiffness equations for spring elements and make sure that we can compare these results to the one we got earlier. So now we understand where we're at and where we're heading. Okay. So the energy method that we're going to use for variational is going to be the minimum potential energy approach. So we're going to use it as an alternative method to derive element equations or element stiffness equations that I'm going to use ESE for them, element stiffness equations, as well as the stiffness matrix K, or for a system would be K. And this approach is more adaptable to the determination of element stiffness equations for complicated elements. As some of the elements we're going to look at later, plane stress strain element. So we're going to 2D. The axisymmetric stress element. A plate bending element. And a three-dimensional solid stress element. It is only applicable to elastic materials, linear behavior. Of course, it is categorized as a variational method. variational method of the finite element method. So what is exactly the principle of the minimum potential energy? The principle of minimum potential energy states that of all the geometric possible shapes that a body can assume, and of course we know that when a body is acted upon, flexible bodies are acted upon by forces, they deform, right? So this is what I mean by geometric possible shape that a body can assume. The true one out of all possibilities, corresponding to the satisfaction of stable equilibrium of a body is defined by a minimum value of total potential energy. Oops. Let's put that in terms of equation. This total potential energy is the sum of the internal strain energy and the potential energy of external forces. So this is what we mean by total potential energy. In terms of equations, I can write the total potential energy as pi sub p, and I write this as equal to u plus omega, where pi p is the total potential energy, u is the strain energy, and omega is that potential force or potential energy of external forces. U is a capacity of, sorry, of the internal forces or stresses to do work through deformation, so forces and deformation. Or if I'm looking at stresses, I will be looking at strains. So this is deformations and strains in the structure. While omega is the capacity of the external forces, such as body forces, of course, like gravity, surface traction, or applied forces, to work through the deformation of the structure. And based on the potential energy approach, if we want to solve the problem, if we know the total or can calculate the total potential energy, if I take the derivative of the total potential energy with respect to any displacement di or nodal displacement di, the outcome should be 0. This is the minimum potential energy approach. Of course, where di is the nodal displacements from I equal 1 to I equal n, where n is the total degrees of freedom. So let's apply this approach to our spring element. So in order to apply the approach, we need to identify the strain energy as well as the potential energy of external forces for a spring. So if I look at the spring element, or a spring that has a spring stiffness K, looking here at it fixed at one end. If I apply a force F, the spring is going to go through an elongation X as I apply. So this is going to extend to a distance X. I may represent for a linear spring this relationship using a graph. But if this is F and this is X, oh, I'm sorry. Thank you. As I apply the force F, starting from a displacement of 0, I get this linear function where I can say that at F max, the displacement is equal to X max. Now the slope of this curve, if this is 1, this is K. Now if I know X max at F max, we can say that K is equal to F max divided by X max. Or I can write this function as F is equal to K times X equal to F max over X max times X. If I want to evaluate the external work done by F, I can say that the work, the external WE, is equal to the integral of F dx. But if I'm going from 0 to X max, and I substitute for F, I can put here F max over X max times X dx. But I can take the constants outside and say WE is equal to F max over X max, the integral from 0 to X max of X dx, which is equal to F max over X max, X squared over 2 from 0 to X max. This is equal to F max. Of course, you can see here we get X max squared and X max. So I end up with X max divided by 2. If you look at this, we can see that the external, this is the area of this triangle, right? So the external work is given by the area under the force deformation curve, where the slope is equal to the spring constant K. Now, from the conservation of mechanical energy, we know that the strain energy is equal to the external work done. Which is equal to F max X max over 2. Now F max is equal to K times X max. So I can come here and say U is equal to F max. For F max, I'm going to substitute that by Kx max. Kx max. And I have here an X max. So that was going to be X max squared over 2. So we'll take this as our strain energy. Next, we want to look at the potential energy of the external force. Now, when I described here the spring, of course, the positive X direction is in the direction of F. So this is my positive X direction. This potential energy of external forces, omega, is equal to, if I have a force F max applied, F max is moved a distance X max. So it's want to go back in the opposite direction. So that would be multiplied by minus X max. So I put here minus F max times X max. So I have an expression for U. I have an expression for omega. The total potential energy pi p is equal to U plus omega, which equal to K X max squared over 2 plus a minus F max X max from here. For any deformation of a spring X corresponding to any force F I'm sorry. To any force F, we simply replace X max with X and F max with F. So I will come here in my equation, and to give a general expression, I would say pi p is equal to, looking here at X max squared, I'm going to write it as 1/2 k X squared. And here I have a minus. I'm going to replace F max with an F and X max with an X. So I have an expression of total potential energy in terms of X. Now we are going to apply that to our spring element. So we're going to consider the linear spring element that has 2 degrees of freedom, or 2 nodes, 1 degree of freedom per node, 2 nodes or 2 degrees of freedom. Yeah, so subject to nodal forces. And these were expressed by F. So if I sketch that, this is my spring element, node 1, node 2. This is my X direction. We had F1 and F2. And corresponding to these nodal forces, we had degree of freedom U1 and a degree of freedom U2. I can write my total potential energy expressed as pi p is equal to 1/2 k times delta X. And this may be measured by U2 minus U1. So I have here U2 minus U1 squared. That's the strain energy. And then I have a minus F times X. But here I have 2 forces. So I'm going to write 2 terms. I have a minus, and I have F1 multiplied by its corresponding displacement U1, and I have a minus F2 multiplied by the corresponding displacement U2. So to minimize the total potential energy, we are going to take the derivative with respect to each nodal displacement. So I'm going to apply d pi p with respect to U1.
From the diagram, both U1 and U2 are facing the same direction.
Correct.
So why
positive X direction.
So why do you decide to subtract
Good.
U2 from
Sure.
U1 from U2?
How would you calculate the strain in the spring? You'd look at the change in length, right? So the change in length with respect to the original length. So the formation of the spring is equal to the change in length. How would you measure the change in length? You subtract U2 from U1. because both of them are going in the same direction. So you get the difference. Okay. So now here I'm looking at the partial derivative of the total potential energy with respect to U1. So I get here half K. And of course, I could have expanded the terms here. If I write it as half K times U2 squared minus U1, U2, right? Plus, this is U2 and U1 squared, minus F1, U1 minus F2, U2. So here I have a half times K, and I'm taking it with respect to U1. So I have a 0. Then I have here, this is multiplied by, these are actually 2, right? Minus 2 U1, U2. So I get a minus 2 U2 plus 2 U1, close the bracket. And here I have a minus F1 and a 0. Next, I do the partial derivative with respect to U2. And by the way, we set this to be equal to 0, right? So the partial derivative of the total potential energy with respect to U2, I'm going to have half K. And here I have a 2 U2 minus a 2 U1, close the bracket, 0, and a minus F2 is equal to 0. So we really have two equations that we can simplify. So the first equation, you see I have here a half and a minus 2 and a 2. So I can write that as a K. And I'm just going to change the order. So I'm going to have a U1 minus U2. And I'm going to move F1 to the other side, is equal to F1. For the second equation, I'm going to have a K multiplied by U2 minus U1 is equal to F2. I can rewrite this as K U1 minus K U2 is equal to F1. And the second equation, I can write it as minus K U1 plus K U2 is equal to F2. Sorry. In matrix form, you can write it as K minus K minus K and K times U1, U2 is equal to F1, F2. If you compare that to K times U equal to F, we find that the stiffness matrix of the spring element K is equal to K minus K minus K and K, which is what we found earlier. Identical to K that was derived using the direct stiffness method. Now, you may think using the direct stiffness method was more intuitive. We just applied equilibrium, was straightforward. Yes, indeed. And we used it to understand and visualize what's going on. But the energy method is going to come handy for more complex elements, as I mentioned at the beginning. So that's why there is importance in learning these methods. And you're going to see how we're going to need them and apply them as we move on into the course and use more elements. Any questions so far? Okay, while this is fresh, let's apply this concept to a more involved problem, similar to what you're going to be doing for the homework. So we're going to look at a system rather than an element of an assemblage of 3 spring elements in series. So we have 3 springs elements connected in series, and they are fixed at the beginning and at the end, node 1 and node 2. 3 elements, 1, 2, and 3. Element 1 has a spring stiffness, K1, that is equal to 1,000 pounds per inch. Element 2 has a spring constant of 2,000 pounds per inch. And element 3 has a K3 of 3,000 pounds per inch. Now, element 1, I'm going to mark my nodes or degrees of freedom, extends from node 1 to node 3, and element 2 from 3 to 4, and element 3 from 4 to 2. So the numbering here, if I'm writing this as a finite element using finite element method, and I want to use a sparse matrix, I would number it differently. I would go like 1, 2, 3, 4. But let's work with this. All right. So we want to use, oh, I forgot to mention here that there is an external force applied at node 4. We have an external force F that is equal to 5,000 pounds. We want to use the minimum potential energy method to develop the elements, or rather the global here, global stiffness equations. So the stiffness equations of the system. And of course, we can use the direct method to quickly assemble the stiffness matrix, the global stiffness matrix for this system like we've done earlier. But we want to apply the energy method. So we want to start by looking at strain energy for each of the elements. So we're going to start by looking at the strain energy, U. So I'm going to go with element 1. And this is this spring here that extends from 1 to 3 as the spring stiffness K1 and degrees of freedom U1 and U3. So I can write U for element 1 as equal to the area under the curve, or K1 multiplied by U3 minus U1 squared over 2. which I can expand it and say U for element 1 is equal to K1 over 2 multiplied by U3 squared minus 2 U1 U3 plus U1 squared. Can apply the same concepts to the other elements. I can go like element 2, and I can say that U2 is equal to K2 over 2. And then if I look at element 2, it extends between 3 and 4. Between 3 and 4. So I'm going to go like U4 squared minus 2 U3 U4 plus U3 squared. Likewise, for element 3, I'm going to get a U for element 3 that is equal to K3 over 2. And element 3 extends from 4 to 2. So I get U2 squared minus 2 U4 U2 plus U4 squared. Now, of course, the total strain energy is going to be the sum of all of these. If I just go to the potential energy, so we can say here U total is equal to U1 plus U2 plus U3. So that was the strain energy. For the potential energy, we're going to have omega equal to, we always have a negative sign, and I have the external forces multiplied by corresponding displacements. So I would have a minus F1 U1, and even though I do not have an applied force, but I could have a support reaction, right? So F1 U1, and let's keep the negative sign outside, plus F2 U2 plus F3 U3 plus F4 U4. Now, total potential energy is equal to U plus omega. I write that as equal to K1 over 2 times U3 minus U1 squared plus K2 over 2 times U4 minus U3 squared plus K3 over 2 multiplied by U2 minus U4 squared. This here represents u. And then for omega, I'm going to write it as minus f1 u1 minus f2 u2 minus f3 u3 minus f4 u4. Now, how many degrees of freedom do we have? We have 4. So we're going to apply the partial derivative 4 times. Okay. So I'm going to do like d pi p with respect to u1. So u1 is here. So when I do this partial derivative, I'm going to get a minus k1 u3 and a plus k1 u1. And of course, you can see this from the expansion like we did earlier. So you get the u3 squared, and we get the minus 2u1 u3.
Excuse me.
Yes.
I was just thinking, assuming there was forces loaded at other points, while writing the potential energy, you put the minus sign, but assuming the forces were loaded and we know the directions of the forces.
Okay. No, good. Because always, if I'm going to say like there is an external force, like clearly there is nothing at 3. But if there was one, I would have made it going in the positive x direction as well.
Okay.
So the potential,
it's always in the positive x direction.
Yeah, we like to do this way so we don't confuse. Okay. So we keep going, and then here I have a minus f1x. I'm sorry, a minus f1 u1. So that would be minus f1 is equal to 0. Likewise, I'm going to do the partial derivative with respect to u2, and I'm going to end up with a k3, and I'm taking the partial derivative and reorganizing. I trust you can all do the details of this. So just the concept here, k3 u2 minus k3 u4 minus f2 is equal to 0. d pi p with respect to u3, I get here a k1 u3 minus k1 u1. No, I think I have this. When we do u3, yeah, we're getting u3 here, and correct. So from element 1 and element 3. From element 1 and element 2. Okay, so I get a k1 u3 minus a k1 u1, and then minus a k2 u4 plus k2 u3, and then I have a minus f3 is equal to 0. And finally, d pi p by d u4 is equal to, and I get a k2 u4 minus a k2 u3 plus k3 u4. I missed one. K2 u4, K2 u3, and then I will put here a minus K3 u2 and a plus K3 u4, then a minus F4 is equal to 0. So I end up with 4 equations that I can write in matrix form as U1, U2, U3, and U4 equal to, we're going to move all the F's to the other side, F1, F2, F3, and F4. And I'm going to start filling in the elements for my global stiffness matrix. So I'm going to come here, and of course, I'm going to put 0 anywhere there are no values. So I'm going to go here, and for the first line, I have a minus K1, column 3. So maybe let me just make some columns. So I have here a minus K1, and I have here a plus K1. For the second equation, I have a K3 times U2 and a minus K3 times U4. For the third line, I have a K1 U3. This was one. And a minus K1 U1, a minus K2 U4, and a plus K2 U3. So there is a K1, and then there is a plus K2 here. For the third line, I have a K2 times U4. I also have a K3 times U4, so K2 plus K3. I have a minus K2 U3, and I have a minus K3 U2. Everywhere else, we're going to put zeros. Now remember, the global stiffness equation or matrix, global stiffness matrix, like the element stiffness matrix, has to be symmetric. Of course, a square, symmetric, and singular. If I look at symmetry, and always the diagonal is going to have positive elements. So if you look at the diagonal, it's all positive. If you look at symmetry, you can see here, this is a symmetric matrix. So this is a good check to make sure we wrote our global stiffness equations in terms of matrices. Of course, I can write this as K times U is equal to F. And please note, I'm using uppercase K and uppercase F because these are global stiffness equations, not element. Now, probably many of you, like myself, I'm going to say, oh, I can do this better by the traditional method of writing the element stiffness matrices and use them to assemble the global stiffness matrix without having to take the partial derivative. And yes, this is true. Probably it is easier. But for other non-standard problems, the minimum potential energy method may come in handy to develop the global stiffness equations. So we're just getting used to all the different tools so we can use them as needed. Okay. This is what you're going to apply for problem 2 in your homework 1, and you should be ready. I think most of you finished either all the homework or at least problem 1 and problem 3. You can now complete problem 2, submit the homework, and when we come back on Thursday, I'm going to start chapter 3. And chapter 3 is going to be lots of fun. We're going to spend probably the most time out of all the chapters on chapter 3, because we're going to establish many of the methods that we're going to apply for more complex elements as we move forward. So get ready that we're going to dive into chapter 3 and be there maybe for 2 or 3 weeks. All right? Okay. I'll see you all on Thursday. Thank you.